Okay, class, so in today's lesson, what we're going to talk about is something called the spring force and how springs or coils are devices that can act as devices to store elastic potential energy. Similar to gravitational potential energy, where if you have some kind of relative height, you have the potential to convert that gravitational potential energy into kinetic energy. What we're going to talk about today is how we can have springs either stretch or compress and store what we call elastic potential energy to also convert into kinetic energy as well. So the first thing I want you guys to take a look at is all four of these diagrams at the very top. I don't know if you can see this or not, but we have identical springs. And just to start things off, what I'm going to do is I'm going to draw a line to use as a reference point. Let me just put this up here. And what that line represents is that if you compare how much the spring has stretched by, in the first diagram you can see that there is no stretch whatsoever. It's at what's called the equilibrium position. So I'm going to say that at this point x is equal to 0. And what exactly is x? Well, x is the amount that the spring either stretches or compresses by. In the next diagram, you can see that we've now applied some kind of a force to that spring, and you can see that the spring has actually stretched by a small amount. That small amount we're going to label as x. In the third diagram, we've now applied a force of 2F, and you can see that the amount of stretch has now been doubled, so therefore 2x. In the last diagram, we've now applied a force of 3F, and you can see that the amount of stretch is now tripled. So what I can now do is graph that relationship on this graph. So we have the applied force on the y-axis, and in this case we're going to say x to represent the amount that the spring stretches by. Now I'm going to point this out here, that even though in this case we're talking about how much the spring stretches by, it could even be a compression. Okay, so it's one or the other. So it's a stretch or a compression, and in this case the applied force that you have on the y-axis is really nothing more than the force applied downwards on the spring. So if we were to attach a mass, let's say for example, if we were to attach a mass to the bottom of that spring, it's the weight of the mass that pulls down on the spring. Conversely, it's the spring that pulls upwards on the mass. And once those two are in equilibrium, we know for a fact that the magnitude of those two forces must be the same. So what we're going to say in this case is that even though I have applied force on the y-axis, it's really nothing more than the spring force. So what would this graph look like? It should be linear. That looks something like this. And as you can see, the line does go through the origin, which has to make sense because if you apply no force on the spring, as we saw in the original diagram, if there's no force over here, there's no stretch or there's no compression. So let's just try this again. If you take a look at that linear relationship, we can write it in the form of an equation y equals mx plus b, whereas in this case y is the variable that you have on the y-axis, which in this case we're going to say spring force. M is of course your slope of that line, and as you can see the slope of that line is it's constant, and in this case because it's a constant we're going to give that slope value a symbol. We're going to give it a symbol k, and of course x is just x, and works out quite nicely because in this case x represents how much the spring compresses or stretches by. Now in this equation we're going to just put a little bubble around there. Again, you don't have to memorize this, it is on your formula sheet. K is often referred to as the spring constant, and what it basically represents is how much the spring is, or I should put it this way, how stiff or how springy, if you will, the actual spring happens to be. Okay? So what we're going to simply say in this case is that if you have a spring constant that's very large, it will happen to be very stiff. Whereas the smaller the value of the spring constant, the more springy it's going to be. If you take a look at the units that we're going to use to measure this the spring constant is newtons per meter, which works out nicely because if you substitute newtons per meter into K, well, X is going to be measured in meters. You can see that the meters cancel out, giving you just the units of meter. Okay, very nice. So that's your simple, that shouldn't be too bad. We'll leave it there for now. If I can have you guys turn the page over. All right, so now in this case, we're going to talk about how that spring force can be used to store energy. So if we take a look at the graph again, we can sort of label any 2 points on that graph. If you take a look at what I have so far here, let me just see if I can zoom in. So what I'm going to say is that if you take a look at the average force that's going to be applied to a particular spring or any mass that's hanging from the spring, that average force can be calculated by taking whatever the initial force is plus whatever the force is when it's compressed or stretched by a certain amount and dividing that value by 2. Well, the initial force, if you take a look at the graph in the previous, on the last page there, the initial force in all of those cases was 0. So if we were to plug in 0, we got 0 plus kx divided by 2, which gives you nothing more than 1/2 times kx. Okay, so, well, if you take a look at the work done, I know for a fact that by definition work is done whenever you apply a force, and that force causes the object to move a certain displacement. So in this case, if work is equal to force times delta D, I could say that work is equal to force times x, which in this case x represents how much the spring is going to be compressed or stretched by. So if work is equal to force times x and the average force is equal to 1/2 times kx, I now get 1/2 kx times x, which gives me 1/2 kx squared. And in this case, the work that's being done is a result of elastic potential energy. So the equation for elastic potential energy is simply just 1/2 kx squared. Once again, this will also be measured in joules. Okay, so what have we talked about so far? Well, we've talked about kinetic energy, gravitational potential energy, and now elastic potential energy as well. So how can we use this elastic potential energy in certain problem-solving type questions? Well, let's see if we can do some examples here. So if you take a look at this diagram on the right, you can see that we have a spring that is attached to some kind of a wall, and right now it's not really resting, but I guess you can say it's resting on a frictionless table. And we're going to say that right now, because there is no mass attached to the end there, the spring is not being pushed, it's not being pulled out. So right now it is in equilibrium, which means it's not stretched or it's not compressed. Therefore, x is equal to 0. So let's suppose that I take a mass or some kind of a block and I push it with my hand to force that spring to compress by some amount. So as you can see, compared to its original equilibrium position, it has been compressed by amount equal to x. And if I just hold that block there, you can see that the spring is right now not moving. So since it's not moving, it must have 0 kinetic energy, but it does have this stored elastic potential energy, which is equal to 1/2 kx squared. So let's say that I now take this block and release it with my hand. Well, the moment that I release it, what happens is the spring all of a sudden stretches back out to its regular equilibrium position, and it now forces that block to leave the spring with some kind of kinetic energy. So the spring, since it's now back into its equilibrium position, it does have an elastic potential energy of 0. And since the block leaves with some kinetic energy, we know for a fact that whatever elastic potential energy we had initially has now been converted into kinetic energy of the block, which is 1/2 mv squared. So let's take a look at our law of conservation of energy from before. I don't know if you guys remember this or not, but from before we did mention that the sum of all your energy at one point, let's call it initially, has to be equal to the sum of all your energy finally. Okay, so in this example over here, we can now say that all your all your energy initially will have to be in the form of one of these three, and all your energy finally must be in the form of one of these three over here. So the question is, which one of these energies do we have at any given point of that for that particular block? Well, if you take a look at the first example over here, as you can see, we have right now no elastic potential energy, we have no kinetic energy, and we have no gravitational potential energy, assuming that the block is at the reference point right now. In this example over here, we have no kinetic energy, no gravitational potential energy, just elastic potential energy. And in this example over here, we have no elastic potential energy because there's no stretch or there's no compression. We only have kinetic energy, and again, no gravitational potential energy because once again, we have no height. So here's the thing. How can we use this to solve some questions in your book? If you turn the page over one more time, let's take a look at the first sample question. It says that a 0.5 kilogram block rests on a horizontal frictionless surface as in the figure from before. The block is pressed against a light spring having a spring constant of 80 newtons per meter. The spring is compressed a distance of 2 centimeters and released. Find the speed of the block when the block is at the x equals 0 position. And again, keep in mind x equals 0 basically means that we are at the equilibrium position. So let's start things off all over again. I'm going to start off by saying that I know for a fact that the sum of all my energy at one point initially has to be equal to the sum of all my energy at some other point finally. So let's just say that the initial condition is the point when the block compresses the spring. So when it compresses the spring, what's the only form of energy that we have? Well, we only have elastic potential energy, and that's initially. So what do we have when the block is now released? When the spring is released, thereby going back to its equilibrium position. Well, once the spring is now at its equilibrium position, it no longer has any compression, so there's no elastic potential energy. It's all been converted into the kinetic energy of the block. So we're going to write down EK finally. So let's write down the equations that we know. For elastic potential energy, we know we have 1/2 kx squared. I'm going to put down a subscript of I to represent the initial compression. And since I have kinetic energy when the block is released, I now have 1/2 mv squared. And I'll put a subscript of f for the final speed of that block. I think you guys can all recognize that we can eliminate the 1/2 on both sides of the equation, and let's just plug in the variables that we know so far. The spring constant, like you said, was 80 newtons per meter. It did say that the spring is compressed by 2 centimeters, so therefore 0.02 meters. Don't forget that's got to be squared. And all of that's got to be equal to the mass of the block, 0.50 kilograms, times the final speed of that block squared. So if you just do a quick calculation, let's just see what the final speed of the block turns out to be. And after a quick little calculation, you end up with an answer of 0.25 meters per second. And that's your final answer. Okay. One thing I want you guys to recognize also is our definition of the spring constant from early on. If you take a look, the spring constant of the spring in this example is 80 newtons per meter. Let's just think about this for a second. What would happen if the spring constant were a bit greater than 80 newtons per meter? So for example, what if we had a spring constant of, let's say, just 100 newtons per meter? Well, let's take a look. If the spring constant were greater on this side, what would that ultimately do to your final speed of the block? Well, keep this in mind. A larger spring constant means that the spring is a bit stiffer or stronger, I should say. And if it's stiffer or stronger, that means that the object should leave with a higher speed. Well, if you did use a higher value instead of 80, you do actually end up with a faster speed coming off that spring. So just a little thing I want you guys to keep in mind, especially for multiple choice questions later on. Let's do another sample question here. We have a 70 kilogram daredevil attached by his ankles to a bungee cord with an unstretched length of 15 meters who drops from the top of a 50-meter high bridge. Keep in mind that the bungee cord in this case is your spring. The only thing is that in this case, that spring or that bungee cord can only stretch, it can't compress. So the cord stops him at water level as shown in the diagram. Assuming that he is 2 meters tall, find the spring constant of the bungee cord. Class, keep in mind that this diagram doesn't really accurately depict what's actually happening. Keep in mind it's not a scale diagram. What they're basically saying is that the bungee cord itself is 15 meters in length. When this person jumps, that person happens to stretch it by an extra 33 meters. And since since the person is 2 meters tall, his head will just barely touch the water surface. All right. So you have to keep in mind, we're going to assume that the point that we're interested in is the point where I guess the bungee cord is attached to this person's ankles. So let's start things off really quickly. If it's okay with you guys, just to sort of do things from the law of conservation of energy perspective, let's label 2 points here. And let me just zoom in actually. Okay, I'm going to label 2 points. I'm going to label the point at the very top where the bungee cord is attached to the bridge to be point A, and the point where the person reaches the lowest point, which is I guess the point where the ankles are attached to this person, I'm going to label that to be point B. Okay, so let's take a look at things from the law of conservation of energy perspective again. Ooh, excuse me. So let's take a look here. We have the sum of all my energy at point A must be equal to the sum of all my energy at point B. Oh yeah, I forgot. We must choose a reference point. What would you guys like to use? Well, I guess it doesn't really matter. If it's okay with you guys, I'm going to try to use the lowest point to be the reference point. So in this case, I will label this point down here to be my reference point or my zero height. Okay? So with respect to my reference point, let's ask ourselves, what do I have at point A? At point A, do I have height? Yes, I do. That means I must have gravitational potential energy. So at point A, I do have mgh. Okay. Ask yourself this question: do you have any kinetic energy at point A? Are you moving at point A? Well, it says that he just drops at this point, so there must be no kinetic energy, and there can't be any spring energy either because, well, the bungee cord hasn't stretched yet. So all we have at this point is gravitational potential energy. So what about at point B? At point B, I'm at the lowest point, so there cannot be any gravitational potential energy. I'm already at the reference point. What about kinetic energy? Well, since I'm not moving at the lowest point, there's no kinetic energy either. So what do I have? Well, I think most of you can see that at this point, the only thing that we have in this system is elastic potential energy, which is 1/2 kx squared. So how do we know we have elastic potential energy? Well, let's take a look. The bungee cord has now been stretched by 33 meters. Okay, so let's just take a look at this equation now and see if we can solve the question. Let me zoom out a little bit here. The daredevil we know is a 70 kilogram daredevil, so we can plug that in for the mass. Assuming this is happening on Earth, 9.8 newtons per kilogram. The height at point A with respect to the reference point, well, 33 plus 15. I think you can, let's do a quick 48 meters. All right. And all of that's got to be equal to 1/2 times k, which we're supposed to find, times x. Now, in this case, x is the amount that the bungee cord has been stretched by, and it's been 33 meters. And don't forget that's got to be squared. Okay, I think we're ready to solve this. So if you work everything out, you should be able to solve for k. And it turns out to be about 60.5 newtons per meter. And there's the value for the spring constant of the bungee cord. Okay. Alright, so I've given you 2 examples for this lesson. I don't want to make this lesson drag on too long, so Please, class, continue by finishing off bullet number 5. Don't forget you guys have your quiz on Tuesday, and please come prepared on Monday with all your questions. If you want the answers to the questions from homework, please make sure you check the solution manual that I posted for you guys. Or I think I posted for you guys anyway. If I haven't done that, I'll do that right now anyway. So in any case, enjoy the rest of your weekend. We'll see you guys on Monday. Bye-bye.